get started. So I am Steve Byrne. I am the director of the Monument Institute here at the city. Some of you may not know about us, so I thought I would just say a few words about the Institute. So we are an endowed institute. We have been doing fundraising like mad. Our pledge is up to $20 million now. And what that means is that we can probably continue running for another, I don't know, 100 years or so, maybe longer. And what we do with these funds is we fund students, we fund postdocs, we fund lecture series, and of course workshops like this. And I hope you enjoy this one very much. I should mention maybe one more thing, that in fact our benefactor will be here for lunch, and he'll be very easy to identify. He's the one not dressed like you guys. Anyway, our next speaker is Douglas Stanford, and he's going to tell us about entanglement-wedge reconstructions using the Petz map.
Okay, thanks. Yeah, it's a pleasure to be here. I did change the topic of my talk yesterday. It was going to be about JT supergravity and the ensembles of random matrix theory. You guys can ask me questions about either talk. So there's a basic question in ADS CFT in holography, which is how much of the bulk does a given boundary region describe? And a few years ago, 3 or 4 years ago, there was some reasonable amount of debate about the following kind of prototypical case for this question. So what I'm drawing here is a spatial slice of ADS3. And let's imagine that we divide the boundary up as follows. We take this red region here, these two red regions, and I'll call these red regions R. R for red at the moment. And the other regions we'll call, this is honestly just pure luck, B for blue. And then what we're going to draw in the bulk are the minimal surfaces that are bounding those regions. So there's obvious minimal surfaces that look like this. Okay. And it's sort of obvious using the wave equation and simple bulk physics that operators inside this region, let's say, can be reconstructed using this red region. Operators inside this region can be reconstructed using the blue region, and so on. But from that perspective, it's not very obvious how to reconstruct operators in here using just red or blue regions. However, there was a conjecture that the operators in the interior of this region here, so let's imagine we have some spin here, that thing is actually described by the red regions because it's inside the entanglement wedge of the joint red regions. So these two black curves here are the entangling surfaces, the surfaces you would use in the Ryu-Takenagi formula to compute the entropy of the two red regions. And the conjecture, the entanglement wedge reconstruction conjecture, said that any operator inside that region could be reconstructed using the red regions. So that the answer to the question, how much of the bulk is described by a given boundary region, the answer was supposed to be every part of the bulk up to the Ryu-Takenagi surface for that boundary region. Okay, so that's the entanglement wedge reconstruction conjecture. And there was some debate about this, whether the spin is really encoded in this region or not. And this question was really settled in a paper by Faulkner, Lukowitz, and Maldacena.
That's just a large N statement.
Sorry?
That's just a large N.
Yeah, so actually there are corrections to entanglement wedge reconstruction that we'll have an opportunity to discuss later at finite n, but for the moment we're discussing this at large n. So the Faulkner-Lukowitz-Maldacena paper showed that the entropy of a boundary region is equal to the RT formula, the area, divided by 4g Newton, plus a correction term, which is the bulk entropy inside the entanglement wedge. And this formula really settles the question. It settles the question in the following way. Let's take this spin here. I'll direct green. And let's put it in an entangled state, where it's entangled with some other system we'll call X. Okay? And now let's compute the entropy. Let's compute the mutual information between the the red regions, R, and X. So this is a sum of three terms. S of R plus S of X minus S of R union X. And we can use the FLM formula to compute these terms. So S of R has a contribution from, so that's the red region here. S of R has a contribution from these two surfaces, the RT surfaces. And it also has a contribution, which is the bulk entropy inside this region, everywhere inside this region. I'll delete these lines now in case it's causing confusion. So the bulk region that we're describing is everything here. And in particular, it has a contribution from this spin here in the center of the space. So this S of R will be some S contribution just from these surfaces without the spin, plus log 2 for the spin. Okay, entropy of X is just going to be the entropy of a maximally entangled state of the spin, which is log 2. And then entropy of R and X together, the entangled spin will not contribute because it's in a pure state between the bulk here and X. So this will be just minus the entropy, forgetting about the spin. So the result is 2 times log 2. Okay. And that implies, so 2 log 2 is the maximal mutual information that any system can have with a single qubit. And what that implies is that the purification of this qubit is contained in the red system R. So the R system contains the purification of this X. What is the purification of X? Well, it's the qubit in the center of the bulk. So that implies that the R system contains the qubit in the center of the bulk. So it describes that qubit. In making this statement, we relied on some, it's not very hard to prove, but some quantum information statements. In particular, that the maximal mutual information implies that R contains a purification of that system. So that's some quantum information fact I'm not going to explain. It's not very hard to prove, but it's true. And given that statement, we conclude that the R system does contain this qubit in the center of the space. Okay. So this is why just knowing the FLM formula, we can answer the question of whether we can answer the question affirmatively, the entanglement wedge reconstruction is possible. Okay, but then we have a question, how actually do you reconstruct the qubit from R? So there have been a few ideas that have been discussed in the literature for doing this. One idea, this was discussed in the JLMS paper, Jeffress, Lukowitz, Maldacena, and Su, and also by Lukowitz and Faulkner, is to use modular flow. I'm not going to comment on that in this talk, but it's an interesting idea. Another strategy for doing this has been to use something called a universal recovery channel, which is the example of that we're going to use is the Petz map. And this is, well, it's essentially a general purpose quantum information tool for doing this type of task. Okay. And the suggestion of using this Petz map in this context was made in a paper by Kotler, Hayden, Pennington, Salton, Swingle, and Walter. And the flavor of their argument was the following. So you do some bulk calculation, like the one that we just did, which implies that entropies come out, I'm going to be very informal here, come out right, which means essentially that the conclusion you come to by computing some entropies is that reconstruction should be possible. So you use a bulk calculation to compute some quantum information theoretic quantities, and then you use your knowledge of quantum information theory, then use quantum information theory to show that this Petz map should work. Okay, but it doesn't really show why it works. You do the bulk calculation, you find that it should be possible using quantum information results and the entropies that you compute. So what I'm going to discuss in this talk is you just do a bulk calculation that directly shows that the Petz map works. And the bulk calculation, it shouldn't be a surprise, but the bulk calculation is very similar to the FLM calculation. So one is sort of removing an intermediate step. Rather than taking the results of an FLM calculation and then feeding them into quantum information theory to show the Petz map works, you just directly use FLM-like logic to show that the Petz map works. So it's a slightly more direct argument, where a gravitational calculation directly shows that this operator should work without having to know quantum information theory facts. Okay. One reason I think one piece of motivation for this is that I think it should be possible to better understand why entanglement wedge reconstruction is possible using this type of perspective than the more abstract quantum information theory logic. The bulk calculation hopefully will show us in more detail why and how entanglement wedge reconstruction works. And this is an important thing to understand because it's related to how you can extract information from behind the horizon of a black hole. Yeah?
So are these statements still true if there's a small black hole in the middle, small compared to the ADS radius?
Well, that could change a little bit where the entangling surfaces are, but yes, up to that statement. In general, you're allowed to put whatever you want in the bulk, and it can change the boundary, can change the geometry, will change where the entangling surfaces are, and
you're doing some kind of you're doing perturbation theory, right? Otherwise, we don't even know what a surface is. Like it's a big quantum flux. Right?
Oh, sorry. Are you asking if we replace this spin by a black hole, or?
You just put a small black hole in the middle there.
Okay, so somewhere else.
In the black hole or near the black hole or whatever.
Okay.
But something that, by black hole I mean something that's, it appears at leading order and at large n.
Yeah, sure.
Do all these arguments still?
Yes. Well, I mean, the result will still be true, but it can change. The answer can change. The answer can change because the entangling surfaces will be deformed by the existence of this black hole. So suppose, well, I could draw a picture, but you probably understand the point.
Yeah.
There's another question.
You're not precluding that. You're not just doing perturbation theory about the idea.
No. So the conjecture of entanglement wedge reconstruction was general,
Yeah.
and the arguments for it are also general. So yeah, I should have given a more comprehensive bibliography of the origins of the entanglement wedge reconstruction ideas and their proofs, but I wanted to highlight this FLM paper because it's often not, I think, given the credit in this context that it deserves. So that's why I presented it that way. Anyhow, I had nothing to do with any of this, so okay. So in order to discuss the gravitational argument that the Petz map works, well, so in our paper, we give a general argument that the Petz map works, which would apply to situations like the one that Andy described. And I'm not going to give the argument in sort of abstract, general way. I'm going to discuss it in a particular example. Maybe a good example to use would have been this ADS3 example that we just discussed. But it's three-dimensional, and it makes it harder to draw the pictures. So I'm going to do the simplest possible example that I know of, which is a two-dimensional example. And it's the one that we go through with pictures in our paper. So it involves a little bit of setup of the two-dimensional gravity model that we're going to be discussing. But I think it's worthwhile because I think it's the simplest case where you can really draw the replica manifolds and explain the argument. So the model that we'll use is one with the following action. So we take JT gravity action plus a tension term for the total world line length of some end-of-the-world branes. So two classical solutions that will be relevant in this theory. So let me draw them. This one is an Euclidean signature, and the same thing in Lorentzian signature. Okay, so what are we drawing here? The red curves are end-of-the-world branes, and the black curve is a usual ADS boundary. So what I've drawn here, this black curve, you should think of as a constant radius surface in the hyperbolic disk. JT gravity is a theory of negatively curved spaces, hyperbolic spaces. So what this is a piece of hyperbolic space where the black line is a constant radius portion of a circle in the hyperbolic plane, and the red line is a geodesic. It's a geodesic because solutions to the equations of motion for this tension term will be geodesics. So end-of-the-world branes like to follow geodesics, and the other term is just a regulated asymptotic boundary of ADS. So this is a classical solution in Euclidean signature of this theory. If we continue that solution to Lorentzian signature, starting with this slice here, that's this slice, then we find a two-dimensional black hole where there's a end-of-the-world brane behind the horizon. And you might be more comfortable if I make this look more like a normal black hole Penrose diagram by drawing singularities here. They aren't really there in JT gravity, but it might make the diagram easier to understand. So this is a Lorentzian signature classical solution of this theory. This is the Euclidean signature one. Okay, and to make the discussion interesting, we're going to consider the case where the end-of-the-world branes have a large number of possible states, I. So, large number of possible states for these end-of-the-world branes, and we'll take the number of possible states to be an integer k that will be extremely large. It'll be like e to the entropy of the black hole. Yeah? Why is the horizon here? If you analytically continue this trajectory, this constant radius trajectory in hyperbolic space, that's like a Rindler trajectory in ADS2. So it hits the mathematical boundary in 2 points. If you like, we could draw it. I could draw the mathematical boundary of ADS2 here. And then this trajectory is like this one. It's this Rindler, like ADS Rindler trajectory. So that was a better drawing. So let me make a better drawing over here, where I draw the mathematical boundary of the hyperbolic disk. So I guess I should have started with this picture. Well, okay, so this is the hyperbolic disk. Here's a geodesic in the hyperbolic disk, and here's a portion of a constant radius surface of a circle. Is that clear? Okay. Okay, so we have a large number of these possible end-of-the-world branes. And it's helpful to think about a quantum state that you get by taking this geometry here and cutting it along the green line. So if we cut it along the green line, then we get something that looks like this. And I'll use the following notation for this object. So we'll write this as state psi I. And I'll put a hat on it because at the moment it's unnormalized. You can ignore the hat if you want. So this psi I should be interpreted as a state in the boundary theory. So we've taken the boundary theory, that's this black curve here. And the state is associated to cutting through the boundary theory at this point, at this black dot. So you should think of the boundary trajectory here as preparing a state in the boundary theory. That state is identified with cutting here at this black dot. And it's a state where at the other end of this segment, we have a boundary condition with an index I. And that boundary condition in the bulk imposes that the end-of-the-world brane should intersect the boundary at that point. So that's what this state psi I is. It's a state where, from the boundary perspective, we put a condition that end-of-the-world brane should intersect at this point. That's like a boundary condition in the boundary theory. And then we propagate for some time. And that's the state psi I. And approximately looks like this. So just to get some practice with that, let's imagine that what we want to compute is an inner product of two of these states, psi I and psi j. Then the boundary conditions that we'll draw for that are the following. So this is two copies of this segment here glued together to make the inner product, where at one end we have a boundary condition of type I, on the other hand we have a boundary condition of type j. So these are the boundary conditions for computing this inner product. And in the gravity theory, what you're supposed to do to evaluate that is find some bulk geometry that's consistent with these boundary conditions. And what that bulk geometry would be is the following. I've just taken the Euclidean thing that we had over here and put it on its side. So we have this two-dimensional geometry, and you'll notice that the same end of the world brane connects the I index to the J index. So this thing is proportional to delta ij, and it has a factor z1 that we'll agree to define as the JT gravity path integral on this space here. So that was for the inner product of these two unnormalized states. To normalize them, we should divide them by the square root of z1, so this is just a delta ij. Okay, so we're almost done setting up the model. The last thing that we'll do is enrich it slightly further by adding I for some propagating matter fields. And then we can consider more interesting states where, for example, we act with some operator that sources some matter fields. And that will create some fields propagating into the center of the space like this. And correspondingly, we should enrich the set of states that we're interested in by adding a second index here, psi I, comma A, where A labels the type of operator insertions that we put on the boundary. So this will be a state where we have some kind of stuff propagating into the bulk. And similarly over here, I, comma A, J, comma B. We'll put operator A here, operator B here. And it will be convenient to choose our labels for A and B so that this thing is orthogonal in A and B. In other words, such that acting with this operator A here creates a state that we'll call A FT for A field theory on this green slice. And it's a member of a set of orthonormal field theory states indexed by A. So we choose our set of operators that we insert in the boundary here so that on this geometry, they source orthogonal set of field theory states on this slice that we refer to as A field theory. Yeah?
Are you imposing anywhere that the scalar in JT gravity be positive?
No, it won't be too important for this discussion, but it's normally you integrate that scalar over a contour parallel to the imaginary axis.
But in order to have black holes, you have to be restricting it to be positive, right?
No. So the integration contour for the scalar is parallel to the imaginary axis. And the classical solutions, so the boundary conditions will be real values for the scalar, but the integration contour is parallel to the imaginary axis.
Well, but just in the classical theory, if you don't restrict that to be positive, you can make a black hole, let it evaporate, and it just keeps going off to negative energy. This is an old thing in the in the 2D gravity models that if you don't demand that that's scalar be positive, then they're not good models for black hole physics.
Well, the boundary value of the scalar is some positive value. But so we're discussing, maybe you're asking a different question. I thought you were asking a question which is what is the path integral contour in the quantum theory?
I think it's different in the flat space JT gravity and in the AES JT gravity. I think the evolution of the black hole will go to zero temperature black hole.
Oh, you think this is a problem only in...
Could you explain what the problem is that you're worried about?
Well, it's very, I mean, generally I think it's very, and it's come up a lot. So I think it's very important that, you have black holes because you have singularity. And the singularity would usually be where the scalar or into the scalar,
okay.
whatever you're calling it.
I would say here you have black holes because you have horizons. And there's
You
no...
have a horizon because if you can take the Penrose diagram of a black hole, and if you take the singularity, you could just keep going going right through it if you don't call it a singularity.
Well, but the boundary trajectory has a horizon. It's a Rindler-like boundary. So that's the sense in which it's a black hole. You don't have to discuss a singularity. In the JT theory, there's no singularity.
Well, I wouldn't say that Minkowski space was a black hole because you can go. You're talking about observer horizon.
I'm talking about the horizon associated to the regulated boundary. So the trajectory of the regulated boundary in the ADS. As time goes to infinity, it only sees it ends at some finite point. That's this point here.
Yeah.
And so there's a horizon. Yeah. There are other boundary trajectories, like the Maldacena-Chi eternal wormhole, where the boundary, actually there are two boundaries in that case, but we can just focus on one of them. And it follows a non-Rindler trajectory that goes on forever, like this. And that's not a black hole. There's no horizon. So the way you can tell it's a black hole is this. It's connected to the fact that the time is periodic in Euclidean signature, which is another way of saying that something's a black hole. Well, the periodic direction is contractible in Euclidean signature. Yeah.
Psi IAs, we have this A field theory on the right.
Yeah.
I think of this as like a tetrapodic psi I tensor A.
Yeah, well, it's a tensor product in the sense that the independent indices. So to choose a state, we should choose a state of the end of the world brane, and also a type of operators to insert here to create a different state in the bulk.
But can I think of the bulk Hilbert space as factorized into end of the world brane states and field theory excitation states?
At least approximately, yes. So the bulk has a description. Right, in the bulk you have an end of the world brane here, it can be in one of many different states, and the field theory over here could also be in one of many different states.
And it will be important that factorization is not exact? Or?
It's important that these states are not orthogonal, even though they're orthogonal in this approximation. Other questions?
The possible states A I can have might depend on the choice of the boundary condition I.
Oh, so for simplicity, let's choose the end of the world brane states to all look the same to the field theory. So there's the property of the end of the world brane that label I is attached to is something that's invisible to the bulk fields. That's the simplest setting. We could relax that assumption, but this is the easiest thing to think about. Okay, so I don't know whether this is clear, but I hope it is. The states that we're considering, these psi IAs, in the bulk, we have a choice of the end of the world brane state, and then some state of the quantum fields that we'll refer to as A field theory. Okay. And in this talk, we're going to be considering a class of states, capital psi sub A, that are the following states. Okay. So we have an entangled state here, entangled between the system that we've been describing so far. That's the boundary system here, and it will be called B from now on. And we entangle that state, the choice of the end of the world brane in that state, with some other system R. And we consider this entangled state here. So the B and the R are supposed to be analogous to the B and the R systems that I drew in the case of ADS3. And the question that we want to address is the following. Can the state of the field theory, A field theory, be recovered from the R system? So the R system might be a little mysterious at the moment. It's just some system that I've chosen to entangle with B. But if you like, you can think about the R system as some other quantum system, some quantum computer or whatever that we have here, and its state is entangled with the choice of the end of the world brane. So this is the R system, and the B system is the boundary theory that's dual to this bulk. And the question that we want to address is whether the state of the bulk fields can be recovered from the R system. Okay, so to test that, we're supposed to draw entanglement wedges. So let me draw a couple copies of the diagram here. So, and let's think about the entanglement surface, the Ryutakyanagi entanglement surface that we would use if we wanted to compute the entropy of the boundary system here. We could think about computing the entropy of the R system or the boundary system. They're going to have the same result because the overall state is pure. And maybe it's more familiar to try to think about the entanglement surface associated with the boundary system, B. So there's two possible choices. One familiar choice is this extremal surface at the bifurcation surface of the two horizons. And in that case, there are two entanglement wedges. The entanglement wedge of the boundary is this region here. And the entanglement wedge of the complement, the R system, is this region here. So in this case, the entanglement wedge of B is equal to the region outside the black hole. And the entanglement wedge of the R system is this region that's known as the island. And I think that Juan will discuss islands some more in his talk. But it's this region here. And if we use this entangling surface as the Ryutakyanagi surface, we find the entropy that's just the area, the value of the dilaton at that point, which is just the coarse-grained entropy of the black hole, the Bekenstein-Hawking entropy of the black hole. So this is candidate surface 1, candidate extremal surface 1. Okay. Candidate extremal surface 2 is sometimes called the empty set extremal surface. And in that case, the entanglement wedge of the boundary is the whole spacetime. Entanglement wedge of the B system is everything. And the entanglement wedge of the complement, the R system, is nothing. Okay, and now we should ask, if we do choose that to be the RT surface, what will be the entropy that we compute? And for that, we need to use the FLM correction to the Ryutakyanagi formula. The area of the extremal surface, which in this case is trivial, the area is 0, the surface is the empty set, plus the entropy of the bulk. So that was the FLM formula, area over 4g Newton plus entropy of the bulk. The area term is trivial for the surface, but the entropy of the bulk is just the entropy of this end of the world brane, which is in a maximally mixed state. It's entangled with the R system, so its entropy is log of the number of states, log k. So these are our two candidate extremal surfaces, and the prescription in computing holographic entanglement entropy is that you're supposed to take the surface with the least entropy. So in particular, if k is ridiculously large, bigger than e to the entropy of the black hole, then surface 1 wins. And if surface 1 wins, then degrees of freedom in the field theory behind the horizon of the black hole will be encoded in the system R, according to entanglement wedge reconstruction. So the entanglement wedge of R, of this system here, is the red region, this island. And that implies, according to entanglement wedge reconstruction, that the region R should be able to recover field theory information, bulk information, in this island region. Okay, so that's the end of the setup of this model. And I realize it might seem sort of unnatural, like the two intervals in ADS3 is more familiar and easier to think about in some ways. But the good news is that from this point forward, thinking about this model will be easier than ADS3 because the diagrams that we're going to draw are simpler because we're just working in 2 dimensions. Yeah?
So in ADS3, we knew we had a whole graphic description of the boundary degrees of
Yeah.
some sort of derivation of.
Yes.
So what do we know about that for this model?
You mean like for R? Or sorry, could you?
For ADS2 and with the end of the world brain, to what extent do we know that there is a whole graphic?
Well, for the
Kind of whole graphic model in 0 plus 1?
well, SYK is a model that's has elements of that.
But SYK doesn't have a gap, right? It's got all these thin fields, so it's not really a bulk theory of gravity.
Yes, but that's true. That's true. But I think it's not the properties of the boundary theory are not going to be too important. The calculation is all in the bulk, and maybe a better answer to your question is that I'm using this 2-dimensional model to illustrate a general gravitational argument, which applies to the 2-interval case in ADS3 or to any case. So if you don't like the thought of doing holography in 2 dimensions, then that's okay. And you could translate this explanation to a 3-dimensional case. You'll have a little bit more trouble drawing the pictures, but it works. I think it is important that well, does anybody want to ask a clarifying question about the setup of the reconstruction or the entanglement wedges or anything that will help the remainder of the talk be more clear? Yeah.
When you have S equals to log K, is it the entropy of the whole boundary when you're considering? Because you have everything.
Yeah, so that would be the entropy. If this was the extremal surface, then that would be the entropy of the boundary system, which is the same as the entropy of the R system, because the overall state is pure.
Right. Okay.
Yeah.
Could you clarify again to what extent holography isn't informed, as we were saying in this 2-dimensional picture? And I guess I want to drill down a little bit more on your reluctance to just declare SYK as a suitable boundary theory.
Well, I just didn't want to get into that because there are senses in which SYK has a bulk description and senses in which it doesn't. And that's an interesting conversation that's orthogonal to the topic of my talk.
So it wouldn't be necessary to have a precise map to holographic?
Well, no. So the argument, well, the answer that I ended up deciding to give Andy is that the argument that we're making here is a gravitational argument that works in other cases just as well. I'm drawing it in 2 dimensions because the pictures are easier, but the argument is general. So you don't need to worry about whether SYK has like a good bulk or whether there's a better theory than SYK that has a good bulk, because the argument actually applies in any dimension and to any case of entanglement wedge reconstruction. Yeah.
I mean, one could also say that a really clear holographic duality, one, I think it's clear in the sense that the ones in 2 and R has not been there, and one might hope that what you're doing is going to give us a guide to how we could get such a thing.
No, I don't think so.
You don't think it will?
I don't think so. No, I'm just explaining a gravitational argument for the Petz map, and I don't really see how that will help us find good holographic quantum mechanics models. But I feel that this aspect of the conversation is really orthogonal to the talk, and so I'm going to move on. Okay. So we've reviewed the status of entanglement wedge reconstruction, the expectations from the conjecture of entanglement wedge reconstruction for this model, for this situation. And the conjecture is that if K is big enough, then you should be able to reconstruct stuff in here using the R system. And we want to show how that works using a gravitational argument. So we're going to start by discussing a version of this Petz map that Steve branded Petz Light. And it's a ridiculously naive version of the Petz map, but it illustrates an important point. Sorry, I actually forgot to, I forgot to say something before we can get to that. Let me first give a more precise version of the question that we want to ask about whether we can reconstruct that region. So the more precise question is the following. We have some states A field theory, and they're mapping to these states psi A that we defined before in the BR system. And let's imagine that we have some operator OAB, which are the matrix elements of some field theory operator in the field theory. Under this mapping, this operator OAB becomes the following operator. So this is an operator in the BR system, which acts on these states in the way prescribed by acting with the field theory states by this operator O field theory. So this is the map under this encoding of the operator O field theory. Yeah?
Could you write a definition of psi with just an A in it?
Yes, I will rewrite it. Okay. So that's psi A. So it's a state where we have the quantum fields in state A, and we have an entangled state of the brane and the reference system. Okay, so the goal is to find an operator O acting only on system R such that psi A, O, R, psi B is equal to psi A, O, psi B, which is equal to OAB. So we have some encoding in the BR system of our field theory states. There is a corresponding encoded operator O, and we want to find another operator, a version of that operator that only acts in R, but it acts the same way. So it acts on these encoded states in the same way as the operator O. So that's what it would mean. Actually, you want a somewhat stronger condition than this, but this is what we're going to analyze today. This is what it would mean for the purposes of today to be able to reconstruct this operator OAB from the subsystem R. So that's our goal, to find an operator OR with this property. Okay, now we can start to discuss the Petz light. So Petz light is the following naive guess for an operator OR. So operator O is certainly an operator that would satisfy this property. It doesn't act in system R, though. It acts in R and B. So we can make an operator that acts in system R by just tracing that thing over B. That will certainly be something that acts in R. Very unclear at this point whether it does anything reasonable. So in the spirit of making this first pass simple, we're going to consider a small set of field theory states. Just two states, zero field theory and one field theory. This is a state of the bulk fields with no particles present, and this is a state of the fields with one particle present behind the horizon. So let me draw this a little better. So under this encoding, zero field theory maps to psi 0 in the system BR, which is 1 over square root of k, sum over I, psi I 0 I, and it looks something like this. We have some end of the world brane. We have the actual boundary. This is a Euclidean drawing, and no bulk fields. The other state, 1 field theory, maps to psi 1 in BR. And it looks something like this. Where we act with some operator that creates some bulk fields, creates one bulk particle, which is behind the horizon at time t equals 0. So the horizon is, let's say, at this point. And we've acted in such a way as to create some bulk particle behind the horizon. So these are our two states, zero field theory, one field theory, which are embedded in the BR system in this way. Okay, and to make life as simple as possible, what we like to do is find an O for the case where O field theory is just 1, 0. So it acts on the state with no particles present and gives you the state with one particle present. So that's our target operator. That's the O field theory that goes here. We could write a formula for the O using these two states here. And then we can trace it over the system B. And what you find, the Petz light operator, is the following. So this is the candidate operator suggested by this formula. Yeah?
That's why you don't get metric one from the trace. Are you assuming orthogonality here?
Yeah, so when we do the trace, good. So let's imagine doing the trace. We take an outer product of this state and this state here, right? That would be the operator O. So O would be psi A, psi B, but OAB has only one term where A is 1 and B is 0. So we have just an outer product of psi 1, psi 0. Then when we take the trace over the B system, we end up taking the inner products of the B. So we turn the outer product, the trace of the outer product of these B vectors is just an inner product of those vectors. And that's this term here. So that's this inner product here, and it multiplies an actual operator in the R system. Is it hard to read this? Maybe I should have written it higher. Obviously, it's hard to read. I'll try to write things higher in the future. Any other questions about this?
Yeah, sorry. So are you assuming that these psi IAs, psi ABs are autonomous?
No, but the fact that we're using is trace over B of any states psi chi B is equal to chi psi. So that's the fact that we're using to write this that way. The chi and psi don't have to be orthogonal, and actually they better not be if this is non-zero. Okay. So what we're going to do to check if this Petz light operator works is just evaluate this. So I'll write a formula for that now. So this thing, psi A OR psi B is equal to C naught over K squared. Okay, so this term here is the same inner product that we had in the definition of the operator. And this term here is from the actual copies of psi in the state vectors psi A and psi B. So that just comes from plugging this formula for OR into these formulas for the state psi 0 and psi 1. A and B can be either 0 or 1. Okay, so now what we're supposed to do to compute this is interpret these inner products as boundary conditions in gravity, and then see what the gravitational path integral thinks about the answer for this quantity. See what it thinks about this expression. So let's write these two inner products in terms of boundary conditions in gravity. So using the same kind of notation that we used before, the first one will be an inner product where we have operator insertions A and B, and then into the world branes in state I and J. So that was this factor here. The other factor looks like this. We have a 1 here, 0, and also J and I for the end of the world brane. So we can connect these index lines and then erase the explicit variables I and J. So these are the boundary conditions that we're supposed to fill in with some gravity computation. And there are two ways of filling it in. One way looks like this. Sorry for the delay while I'm drawing these pictures. Okay, so these are the two different ways of filling in with geometry these boundary conditions. So now what we have to do is evaluate these two gravitational computations. So whoops, I forgot the index line here. So there's 3 steps in evaluating these guys here. One step is to count the index loops. Another step is to evaluate the contribution from gravity. And then the third step is to evaluate the contribution from the quantum fields propagating on that background. The index loops are very easy. This has one end of the world brane index loop. So this is proportional to 1 factor of k. The gravitational path integral, I'm just going to write sort of a cartoon for the answer. Since we have 2 of these Euclidean black hole geometries, we get something that I'll write as e to the 2 times s, where s is roughly the entropy of the black hole. This is not exactly precise, but good enough for our current discussion. So, and then we'll have some field theory computation to do here. But it's clear that the field theory computation is not going to work out very well because we want the A index to be set equal to 1 and the B index to be set equal to 0, but these things are in separate gravitational spaces. So there's no way the quantum field theory path integral can set the A equal to 1 and the B equal to 0. So the field theory calculation here comes out looking bad for the Petz map computation. In fact, the field theory calculation, as we presented it, will just give 0 because this 1 and 0 state are defined to be orthogonal on this geometry. So this term would give actually 0 in the field theory computation. So k times e to the s, e to the 2s, times 0. Okay, let's look at this geometry here. We have now 2 k index loops. So we have a k squared. We have just one connected geometry. And that gives something that, again, in a rather crude approximation, we can write as just e to the s, not e to the 2s. And then there's some field theory computation that we'll discuss in a second. But let's forget for a moment the field theory computation that gave us 0 over here and that will give us something that we'll discuss in a moment over here. This geometry is proportional, this answer is proportional to k times e to the 2s. This one's proportional to k squared e to the s. So this one will win if k is extremely large. This geometry will dominate if k is extremely large. And in particular, if k is big enough that the entanglement wedge of the R system includes the interior. That was the case where the entanglement wedge of the R system includes the interior. That's the case where this geometry here dominates. Okay. So let's now discuss what this geometry gives us. So let's suppose k is very large so that this geometry dominates, and let's ask what it gives us. What does the field theory computation that we do on this geometry give us? And here's where we see the limitations of the Petz light operator. This was the formula that I erased a second ago was a ridiculously naive formula. And in fact, it does not work for general states. It works for a special class of states that correspond to fixed area states of Akers, Rath, Dong, Harlow, and Marolf. The precise definition of those states won't be super important because we'll discuss the actual Petz map in a moment, where that restriction is not necessary. But what it does is it means that when you glue geometries together like this with multiple asymptotic regions, you glue them together by just taking copies of this geometry with one asymptotic region and then putting some kind of conical excess, a 4 pi, in this case, conical excess at the center. So that for Akers, Rath, Dong, Harlow, Marolf fixed area states, what this geometry really means is a geometry that we can draw as follows. 2 copies of this thing. Uh-oh. With these cuts glued together. If you take these 2 geometries here and glue them together, the top of this cut to the top of that cut, the bottom of this cut to the bottom of that cut, then you're going to make a geometry that looks like this with a 4 pi conical excess at this point. So, okay. Conical excesses are not really the point of this talk, but they're a feature of this geometry for the fixed area state. And that makes it easy to evaluate the quantum field theory computation on this background. We do it as follows. This one operator here creates a particle that by definition of the one operator creates a particle that propagates behind the horizon of the black hole. 0 creates no such particle. So this geometry here looks like this. The one particle has propagated there to the top of the cut, and nothing has propagated to the bottom of the cut. Now when we glue those geometries together, we're going to glue the top of this cut to the top of that cut, so we're going to end up with a particle here. And that particle is going to propagate out to the boundary, to this location, which means that the answer for this will only be non-zero if A is equal to 1 and B is equal to 0. So the particle propagates from this second copy through, goes through the top of this cut, ends up on the top of that cut, and propagates back out to the boundary. And then in order for this amplitude to be non-zero, A has to be 1. There has to be an operator here that will soak up that particle, and no operator creating a particle here. So the quantum field theory answer on this geometry is proportional to delta A comma 1, delta B comma 0. And that is indeed what we would have expected for psi A times the operator that we wanted to make, which was 1, 0. The embedding of this field theory operator. Sorry, I've written a bad thing. But this was the field theory operator we were trying to make. If we embed that thing in the Hilbert space of the BR system by upgrading these to psi 1 and psi 0, then this matrix element would be proportional to this answer, which is indeed what we found from a gravity computation. Okay, so there's a something that I find kind of interesting about this Petz map discussion that is made extra clear in the Petz light case. And that's actually the reason why I wanted to discuss the Petz light case. It's the following. In this computation here, we have two asymptotic regions. We started out with a problem there where there was just one black hole. There was one black hole, and then there was this radiation, this extra system R that was entangled with the black hole. In this computation, that black hole system is this one. This is the black hole. You can tell that's the black hole because that's the physical system with the A and B indices that we're taking the expectation value of an operator inside of those states. So we're taking the matrix element of some operator between states A and B, psi A and psi B. The copy with the A and the B indices reflects the actual state of the system. So this is the physical black hole. What is this copy over here? This copy over here, so in other words, that's this copy, black hole. And these psi A's and psi B's come from these psi A's and psi B's, the bra and the ket that you're actually evaluating the matrix element of the operator between. So these are physical copies. This second copy here comes from the formula for the operator OR. So this is just a set of numbers that somebody is acting on the R system, and we instruct them to use the Petz map. They look up the Petz map. They see that it involves a bunch of these inner products, and just a list of numbers. They put that list of numbers here in their formula for the operator. But that list of numbers has the interpretation of inner products of states in a black hole. So we can think about this list of numbers as being things that they would compute in their quantum computer, maybe by simulating the black hole. They want to apply the Petz map, and they need this list of numbers, which are inner products of states of the black hole. The way they compute them is by setting up a quantum computer to simulate the black hole, and then computing inner products. So the second copy belongs to some quantum computer in the R system. And what's happening here is the black hole system and the quantum computer system get joined together. The gravity path integral joins the two together. And then the particle that ends up in the physical system comes by propagating from the copy associated with the quantum computer. In some sense, this is a fictitious system. It's a version that exists to compute these matrix elements. And the particle that ends up behind the horizon in the physical black hole starts its life at the boundary of this somewhat fictitious system. Okay, yeah.
I'm sure you said it, but I missed what right in the beginning when you put the 4 pi
Yeah.
there. What was the motivation for that?
Yeah, so that was, so there's a class of states that have been discussed by Akers, Rath, Dong, Harlow, and Marolf, where for those states, what you're supposed to do is you're supposed to fix the area of the extremal surface. And since you're fixing the area, you're not integrating over the metric at that point. Since you're not integrating over the metric at that point, or not integrating over the area at that point, that means that you're free to put a conical excess there. So in these types of states, it's okay to have a conical excess at that point. And in fact, so that means that you're allowed to have a 4 pi conical excess. And fixing the area there means that, in fact, you must have such a conical excess in order to construct this geometry. For our purposes, it's really just a trick that in those states, it's very easy to make replicated geometries with multiple asymptotic regions. You just glue the single replica copy together n times and just deal with the conical excess that you get. You just accept the conical excess that you get. So for these two copies, you get a conical excess of 4 pi at that point by gluing two unback-reacted single replica geometries together. So that's a...
Because we've got two things that we don't also get 6 pi and 8 pi.
That's right. So if
They don't start 4 pi.
exactly. So you would have more, if we had more replicas, you'd get 3 replicas, you get 6 pi, 4, you get 8 pi. But this is, for the purposes of this talk, this fixed area states are a somewhat artificial set of states where this crazy simple Petz light formula happens to work. And it's illustrative of the general mechanism for the Petz map. But the general Petz map formula, which I'll discuss next, works without making that assumption. It has a clever way of removing the back reaction. Yeah?
Are these fixed area states natural things in holography? I understand there's a lot of tensor networks, but let's forget about tensor networks. Would you ever think about them?
Well, probably not. I don't know. I'm not sure. I'm not sure. Okay. So let's now discuss the full Petz version. Oh, by the way, sorry. Something I should clarify. This discussion where I was talking about this fictitious quantum computer or whatever and the black hole sounded like we had gotten very far away from the two intervals in ADS-3. Like, why are we talking about quantum computers acting in the Hawking radiation and that kind of stuff? But there's a similar situation in ADS-3. So in order to act with this operator in the B system on the two blue intervals that we were, sorry, our system, the two red intervals that we're supposed to reconstruct the interior, you would act with an operator there that knew about the full system, including the complement, the B system. So you would act with an operator there that had matrix elements defined in the B system. And so there would be a second copy of like the B system at play inside that operator, which is exactly what we found here, a second copy of the B system. Okay. Okay, so let's discuss now the Petz map. It gives us a different formula, which is more general purpose, and it looks like the following. Okay, so you define this operator sigma r. It's like an unnormalized density matrix, which is the trace over B of the projector onto the code subspace. The code subspace just means the span of all these states psi A that we're going to be considering. We took some field theory states A, we embedded them in the full BR system. That's like an embedding of logical qubits in some code. That's the reason for the use of the term code subspace. And this sigma r is defined to be the trace over B of the projector into that full subspace. So we're summing here A equals 1 up to D code, where D code is the number of these psi A states. So it's the number of different bulk states that you're going to try to be able to distinguish from the R system. So that's what sigma r is. And you take it to the minus 1/2 power, trace over B of O. This was this ridiculously naive guess for an operator, and sigma r to the minus 1/2 power. And this is a quantum information theorist approved general purpose map for accomplishing this task. And I think it's amazing that at the core of this operator is such a ridiculous, naive guess for how to build an operator in R that accomplishes the same task as O. Okay, so to compute this thing, what we're going to do is a version of the replica trick, where we define an OR with an index as sigma r to the n, trace B of O, sigma r to the n. And we're going to be interested eventually in the limit n goes to minus 1/2. Not easily, no. It's well, it's a mathematical. What do you mean by whether we can do it on a computer? There are different constraints you might be asking about.
Well, I mean, it's, let's say, quantum channel, the sequence of unitary operations,
Well, this is not. Yeah, it's again, there's different things that you might mean. So in order to okay, so let me make two comments. The first comment, in the spirit of whether it's an operation that's allowable. The operations that are allowable in quantum mechanics are unitary operators. If we start with the unitary operator here, O, then in general the result will not be a unitary operator. However, if this operator acts almost the same way as that one, then we can make unitary operators by exponentiating Hermitians. So if we start with Hermitian operator that does basically the same thing as the Hermitian operator in the other system, then this map preserves hermiticity. So we can make a Hermitian operator we can make a unitary operator that way. So in principle, this gives a recipe for producing something that actually would be a unitary operator. However, the computational complexity of this thing is very high. This trace operation, even by itself, is enough to make it very high. It's like something that could be evaluated using post-selection, but post-selection is not something that's computationally feasible. There's another part of the answer to this question, which is that the Petz map is viewed as a quantum channel. And quantum information theorists, to quantum information theorists, a quantum channel is something that you can actually do. So the adjoint of this map on operators is an actual quantum channel that you can do to states. But it doesn't have the interpretation of operator reconstruction. It's a type of quantum channel where you destroy the BR system altogether and then you create a new version with the new logical state. So the way that a quantum information theorist thinks about this channel is different from the way that we think about it. We want to just act with an operator in the R system and not touch B. We're not willing to completely annihilate the whole system and build a new one with a new logical state embedded inside it. So we have somewhat stronger constraints from that perspective on what's an acceptable operator. And I think the only way to make an acceptable unitary operator, only general way, would be by doing something like exponentiating Hermitians. Okay. Yeah.
operators. So if I conjugate O by some unitary that acts only on B, the Petz map is unaffected. How should I think about that in both?
If you say it again, if you conjugate what by?
O, that operator that's sitting inside trace B, by UB times the identity and the rest,
Mm-hmm.
then doesn't affect OR, and how should I think about that?
Well, I guess it's that this operator somehow, yeah, it cares only about the part of that operator in R. That I think that's the part that I find surprising about this, that like, you might have thought that in order to make a best guess operator in OR, you would care about how your original operator had acted in B. There's a slight subtlety in this, which is that I'm assuming that the operator O preserves the code subspace. And that won't be true for the operators that you're considering. If you take this O and conjugate it by some operator, then in general it won't preserve the code subspace. So that statement isn't exactly true, but there would be a reduced version of it that's still true. Okay. Okay, so this is the replica version of the Petz map operator, and we want to evaluate this to check how well this Petz map operator works. Now, for Petz light, we got some expression involving two of these matrix elements, and we had two boundaries as a result. For full Petz, we're going to get some unpleasant expression here that I'm not going to write with like bunches of these inner products. So what I'll draw instead is this. What it looks like, what the analog of this picture I just erased was. Analog of that picture is the following. They're arranged in a circle where we have A here, B there. A1 indices, these are associated with these sigmas. So these boundaries here, we have n boundaries up here, n boundaries down here. Those are the sigmas, sigma r to the n. AN, AN. Then over here, we have A prime, B prime, O, A prime, B prime. That's this factor here. And then we have a bunch of other sigmas down here. Bn, Bn up to B1, B1. And these guys are all connected by end-of-the-world brane index loops. So that's that. And there's a normalization factor to make all the states normalized, which is 1 over k z1 to the 2n plus 2. Okay, so that's equal to this expression. And our task is now to fill that in with all possible geometries and evaluate the answer. In the limit where k is very large, a completely connected geometry is going to dominate because it will have the maximum number of k index loops. Get the maximum possible number of k index loops by building a geometry that looks like this. This is going to have 2n plus 2 k index loops, which will cancel the factor of k to the 2n plus 2 outside, and then allow us to erase all of the k index loops. Okay, so we still need to compute the gravitational part of the computation here, and then the field theory computation. So the gravity part is at order 1 over g Newton. The field theory part is at order 1. For the gravity part, we don't care about the propagating quantum fields. We care, we can erase all of these A and B indices. So we care only about this geometry here, and that's some object which has, well, it has 2n plus 2 boundaries. So it's proportional to a path integral, we'll call it 2n plus 2 for this path integral with 2n plus 2 boundaries. And we divide it by this normalization factor, z1 to the 2n plus 2. In the limit n goes to minus 1/2, this is equal to 1. So the gravitational contribution just goes away completely in the replica limit, n goes to minus 1/2. What remains is a pure field theory calculation. Pure field theory calculation on a fixed background. It's like the FLM computation. There was a gravitational piece, so they were computing the gravitational entropy. They found a gravitational piece, which was the area, and then the correction at order 1 was a pure field theory calculation on the fixed background. Here we took care of the gravitational piece. It's simpler here. It's just 1. It doesn't give some area term, it's just 1. And what we're left with is some pure field theory calculation. And what we're looking for is the analog of FLM's conclusion that you get the bulk entropy. So their field theory calculation gave the bulk entropy. And what we're looking for now is the analog of that. And unfortunately, I'm running low on time, so I'll have to be a little bit brief. But let me sketch the way that you evaluate the continuation of this computation, this field theory computation, to n equals minus 1/2. The way you do it is you realize that on the fixed background that we encountered at order 1 over g Newton, there's a 2n plus 2 replica symmetry. And so we can divide this geometry up into pieces, 2n plus 2 pieces, where this operator here we'll call an operator in the field theory m, a, b, theta. So it's an operator in the bulk. In the bulk field theory, it acts on the Hilbert space of quantum fields on this slice and gives you, so it takes in a state there and gives you a state here. So it's an operator in that sense. It has boundary conditions that it's willing to accept on the quantum fields on these two slices. This is an operator in the bulk field theory Hilbert space. And the computation that we're trying to do is can be written in terms of those m's. So it's a trace in the bulk field theory Hilbert space of m, a, b, theta. Well, let me not write it in light of time. Sorry about that. It's obviously a product of these m's, a trace of product of these m's. And we want to take that trace of products of the m's and continue it in the parameter little n. We want to take little n to minus 1/2. There's two sources of n dependence in that computation. One source is the explicit number of these factors, right? There's 2n plus 2 of these factors. So that's one source of n dependence. The other source of n dependence is this angle theta. Theta is equal to 2 pi divided by 2n plus 2. And in order to analyze this, we can take one of those sources of n dependence to minus 1/2 before the other one. We want to take them both to minus 1/2. To analyze it, it's convenient to first take theta to 2 pi and leave the number of factors here as equal to n. Then this MAB operator simplifies. The MAB operator becomes the following object. It becomes this object with A here and B here. And this is equal to trace over the outside of the field theory A, B in the field theory. So this is an operator on these two dashed lines here, and it's equal to the trace over the outside of an operator on the full slice, which would have been the A, B outer product. So then we end up with a computation. This thing becomes a computation involving factors of this field theory operator, trace outside of A and B, outer product. And what should I say to cut this short? Well, I'll tell you the punchline. So it's one or two steps. This computation, once you write it in terms of this object, becomes a purely field theory computation. And what that field theory computation is the following. It asks, how well does a different Petz map succeed? We've been doing a Petz map for this gravitationally defined operator. And the gravitational analysis of that reduced to a field theory analysis in the bulk. The field theory analysis, the question that thing is asking is for a different type of Petz map. It's a Petz map for the channel where you trace out the region outside the entanglement wedge. So it says that the reconstruction succeeds as well as a Petz map for a channel where you trace out the region outside the entanglement wedge. And that's exactly the answer that you should expect, because tracing out the region outside the entanglement wedge is equivalent to just being able to describe the stuff inside the entanglement wedge. So the gravitational path integral reduces to a field theory computation that says basically you can reconstruct everything inside the entanglement wedge and nothing outside the entanglement wedge. And that's a general conclusion for any location of the entanglement wedge. So sorry for running out of time. I have trouble explaining this topic somehow, and I always run out of time. So I'm sorry about that. But I guess I'll just stop here. Thank you.